Hey, sorry for not making any videos recently. I've been a little busy. I'll try to go back and kind of fill in some more stuff because I'm skipping from free radical halogenation to EAS reactions, which, what does that stand for again? Something substitution. Electrophilic aromatic substitution. So aromatic rings, or aromatic structures I should say, have a general form of 4n plus 2 number of electrons, so it's going to be I guess we don't have 2, but like 6, then 10, 14, so on and so forth. Anywho, a good example, simple one, an aromatic, hopefully you can see this, is 6-carbon benzene. Yay, with the double bonds there. The reason why, and it's incredibly stable and low energy, the reason why is because the charge, or it's not, the octet rule isn't filled or isn't followed, all the carbons don't have what they want, but the amount of hybridization going on here, not hybridization I should say, resonance forms, allows for it to be a very delocalized charge, so it's much more, it's very stable I should say. That being said, it's very difficult, well I shouldn't say very difficult, there are certain things you must do in order to carry out a reaction on a aromatic ring. Excuse me. One of these things being you have to maintain the aromaticity of the ring, so you can't really screw it up. For example, like if you were to stick on, and this is a very reversible reaction, so I'm going to try to write from your perspective, H+. This double bond is going to attack it, and we'll get same thing, except up here you're going to have your H, and the abandoned carbon gets the charge. That very easily can just go back to that, except you would subtract the H+. They're very interchangeable. So if you wanted to create something along the form of this structure, the D's are just deuterium, which is basically heavy hydrogen. It has an extra proton. Really all you have to do is this kind of reaction, but with a massive excess of deuterium. So you would deuterium, this is going to come attack that. So how does it work exactly? This one's going to have hydrogen and a deuterium on it. And really there's about a 50-50 chance as to which one's going to get knocked off, which is why you have to do this in massive excess to deuterium, so that hopefully these electrons will go back, hydrogen goes off, and you're left with triple bonds again. The aromaticity is still maintained. Really nothing changed if you added on a deuterium. Noting this principle of it, you can use certain electrophiles to add on to aromatic rings. Again, you have to maintain the aromaticity. So certain ones are hydrogen plus, or NO2 plus, any sort of alkyl cation, so basically an R plus, bromine, or Br plus, Cl plus, also sulfuric acid, SO3H, I think that's sulfuric acid, and also carbonyl groups, I think it's carbonyls, yeah. They should all be able to do chemistry on aromatic rings. For example, if you were to take the benzene again, and react it with, I'm going to try to write upside down, hopefully this will work, NO2. Well, it's supposed to be a 2. NO2 plus. The 2 electrons here are going to want to come and attack this, the positive. And what you're going to end up forming due to this is positive charge goes with the abandoned carbon. You have the hydrogen there that's just naturally there. And the NO2. However, between the two of these, hydrogen's much more likely to leave than the NO2 because NO2 wants to stay. So the hydrogen, the electron's going to come down here and make the double bond. Hydrogen goes bye-bye. So we have minus H+. And you're left with, again, the aromaticity is maintained because we remade the double bond here. But you're left with this NO, whatever that number is, NO2 group on here. From here you can do other chemistry and whatnot. So with any of those that I listed earlier, I would write them out, but I'm not sure I can do it upside down. H+, NO, let me do this real quick. NO2 plus, okay, so really any of these listings of electrophiles will work quite well for these EAS reactions. Wow, this is a long video. Okay, I'm going to make a part 2 then, because this is how you add one group, but it brings a whole other question. If you're going to add a second group on there, how does that work? Where does it go? All that stuff. So, yeah.